Hello, this screencast is the second in a series where we will look at transforming the sine and cosine functions. In this video, we will focus on horizontal shifts and their impact on the sine and cosine function. Given the functions k of t equals a times the cosine of the quantity t minus b plus c, and h of t equals a times the sine of the quantity t minus b plus c, we see that k of t and h of t are transformations of the cosine and sine functions, respectively. Previously, we saw that the real number a will cause the cosine and sine graphs to be vertically stretched or reflected over the x-axis when a is less than 0, and that the absolute value of a is the amplitude of the graph. We also saw that the real number c will cause the cosine and sine graphs to be vertically shifted and that the midline is y equals c. From our previous study of transformations, we know that the real number b will horizontally shift the graphs. In the following slides, we will further explore how horizontal shifts impact the graph of y equals the cosine of t and y equals the sine of t. But first, let's quickly recall the properties of the parent functions sine of t and cosine of t. When considering horizontal shifts, we want to focus on the starting point for each of these graphs. When traversing around the unit circle, the sine of t starts at 0, 0 and is increasing. That is, the sine of t starts at its midline and is increasing, while the cosine of t starts at its maximum of 0, 1. Then we can also recall that the amplitude of both of these functions is 1, which is the radius of the unit circle. The midline, y equals 0, is the y-coordinate of the unit circle's center, and the period, 2 pi, is the circumference of the unit circle. Also notice that the range of the sine of t and cosine of t is negative 1 to 1. Now let's look at some cosine and sine functions that have been horizontally shifted. On the left, we see the graph of k of t equals the cosine of the quantity t minus pi over 2, and observe that it is a horizontal shift right of pi over 2 units of the parent function cosine of t. In yellow, we see the graph of cosine of t and know that the starting point is 0, 1. The starting point 0, 1 has shifted right and is now at pi over 2, 1, as a result of the horizontal shift. We call this new transformed point the anchor point. So the anchor point for the transformed function k of t is pi over 2, 1. Now let's look at the graph on the right. H of t equals the sine of the quantity t plus pi. We observe that this graph is the result of shifting the sine of t to the left pi units. In yellow, we see the graph of sine of t and know that the starting point is 0, 0. The starting point 0, 0 has shifted left and is now at negative pi, 0 as a result of the horizontal shift. So the anchor point for the transformed function h of t is negative pi, 0. Let's now look at an example where we perform a horizontal shift as well as a vertical stretch and a vertical shift to the graph of a circular function. Here we want to describe the graph of k of t equals 1/2 times the sine of the quantity t minus pi minus 2 as transformations of f of t equals cosine of t. In addition, state the amplitude, midline, period, and range of k of t. Pause the video and try to answer this question on your own. Alright, so we know that the first transformation is a horizontal shift right pi units. This tells us that the anchor point will have a t-coordinate of pi. The second transformation is a vertical compression by a factor of 1/2. This means the amplitude is 1/2. The last transformation is a shift down 2 units, making the midline y equals negative 2. Previously, we saw that vertical stretches and shifts do not impact the period, and nor do horizontal shifts, so the period is still 2 pi. We also saw that both vertical stretches and vertical shifts impact the range. So it helps if we recall that half the curve lies above and half the curve lies below the midline of y equals negative 2. Given the amplitude of 1/2, we can conclude that the lowest output value the graph reaches is negative 2 minus 1/2, which equals negative 2.5. And the highest output value the graph reaches is negative 2 plus 1/2, which equals negative 1.5. So the range of the graph is -2.5, -1.5. Lastly, because we know that the cosine of t normally starts at its maximum, we know that the output coordinate of the anchor point is the maximum value we found in the range, -1.5. And here is a graph to confirm our findings. We can verify that the amplitude is 1/2, the midline is y equals -2, the period is still 2 pi, and the range is -2.5, -1.5. And the anchor point is at pi -1.5. Let's look at one more example. Describe how the function h of t, graphed below, is the result of transforming g of t equals the sine of t. In addition, state the amplitude, midline, period, and range of h of t, and write a formula for h of t. Pause the video here and try to answer this question on your own. Alright, so in this case, it helps to first identify the properties of the graph and then use those to describe the transformations. First, we should look at the anchor point. The sine function normally starts at 0, 0, which is the midline of the graph, and is increasing. Here we notice that the midline is y equals -1, and the first time the graph intersects the midline and is increasing is at t equals pi over 2. This tells us the anchor point is at pi over 2, -1. It also tells us that the sine of t was shifted to the right pi over 2 units, and shifted down 1 unit. Next, we notice that the amplitude is 1/2, which tells us the graph of sine of t was vertically compressed by 1/2. We also observe that the period is 2 pi, and the range is -1.5, -1/2. Putting together these transformations, we can conclude that a formula for h of t is 1/2 times the sine of the quantity t minus pi over 2 minus 1. In conclusion, we saw that multiplying the cosine and sine functions by a factor of a applies a vertical stretch or reflection across the x-axis, and that a vertical stretch determines the amplitude of the transformed function. We also saw that adding the real number c to the cosine or sine functions applies a vertical shift, and that a vertical shift determines the midline of the transformed function. By starting at the midline y equals c and subtracting the amplitude, we get the lower value of the range, and by adding the amplitude, we get the upper value for the range. Finally, we saw that the real number b applies a horizontal shift to the sine or cosine function. The anchor point for the cosine function has a t value that is equal in value and direction of the horizontal shift, and the output is determined by adding the amplitude to the midline. While for the sine function, the anchor point has a t value that is also equal in value and direction of the horizontal shift, but the output is determined by the location of the midline. In the next video, we will look at a new transformation, horizontal scaling, and see how that affects the graphs of this cosine and sine function.